Let's check whether, yeah. Today's very nice school because I really had Professor Oliver. And also made a lot of new contacts for the future, so therefore, thank you very much for inviting me. So my first lecture. So on what one could do in neuroscience when it comes to metastability. Metastability is something which is not only known in neuroscience. Now again, this thing is blocked. I checked it, of course, in the page. Now it's not working. We can do it this way. Okay, fine. So let me give you a brief motivation. So this is just the motivation, only with examples from different papers from the literature. So you see also the authors here and the papers where these pictures come from. So what is usually associated to metastability? It means that we have changing patterns. So of activity, of neural activity in very different contexts. So there are four basically randomly chosen examples here. One would be so-called EEG microstates, so which are recordings of subjects with eyes closed, so to say this is a kind of resting state, or we have firing activity which is either, so to say, happening, or there is silence, so there is this kind of exchange between silent periods and firing periods. So this is something, so where you see it's in the cortex of the rats. Then we have also something which you can see that bursts are generating after the stimulation of this central pattern generator with some signal. And so then all of a sudden, so to say, as a response of the stimulation, so you see a certain pattern appearing, which finally disappears again. Or so then there is seizure-like activity, which is also stimulated as a response, so to say, to some drug which was given. And again, it shows that there is some change in the dynamics of the patterns. So what you see is that some of them are spontaneous, others are stimulus evoked. So that means, so this type of dynamics where you have a change between different patterns can be either, so to say, something which comes out of the blue in a certain sense. It can be the response of some particular treatment of neuronal tissue. So the question is, and this is what I would like to tackle, can we find a kind of framework which helps understanding all these very different patterns, or patterns changing, I would say, so to say, under a certain umbrella, so that we look at transitional phenomena from a common point of view. So can we construct this kind of common view on mechanisms, so which we would call then metastability? Because when you look into the literature in neuroscience, lots of different ideas what is metastability, and people try to find different definitions, which on the first side, so to say, at first glance, they would be somehow similar, but then there are specific properties coming in these type of definitions. So for instance, we see there the variability of activity patterns, which is on the left. So this would be an observation where we have different time intervals in which different activity takes place. Then metastability in neuroscience is also related with that we have a kind of variability of regimes. So that is also dynamical behavior, which is changing, having different properties. So you go between different states of the property. So then this would be now on the top, so to say, in the middle. But so you find also papers where people discuss that there is this kind of stability landscape, which we already discussed when we were talking about bifurcations. So, and then these changes within such a stability landscape, so to say, going down more or less to different valleys, would also be called metastability. The second row here, so then this is related with synchronization patterns. So you have either variability, so to say, in synchronization, that it is for some time, some things are synchronized, then there are unsynchronized, there's unsynchronized behavior in time. So this could also be for certain periods, and then something else happens. And there could be variability in state space, so that you have associated more or less different regions in state space with some different behavior. This would also be called metastability. And finally, so this concept of integration and segregation, which is understood as, so you have basically connected areas, say, of neuronal tissue, and then so you change from synchronized patterns to non-synchronized patterns. So all of this you find under the name of metastability, and usually people are really, so to say, focus on specific properties. So what type of dynamics is that? And what you see also in the last row is, again, so there is a debate whether metastability is only spontaneous or it is driven. So you evoke some changes in patterns, and then it would be a driven process. So what would you count as metastability and what would you not count as metastability? So there are different opinions in the literature. Or does it have to be repeatable so that you are jumping all the time from state to state? Or it's non-repeatable that you never come back to the state where you have been already? So all of this is practically a whole bunch of ideas. And what I would like to do now is that I would like to try to put this in a kind of framework where we can tackle all these cases as, so to say, special cases, but from a more general point of view. And which is only related to neuroscience, because there is also a lot of activity now going on in climate science to, for instance, also explain the observation of different weather patterns in the framework of metastability. So can we come up with something which is more common and gives rise to so to say, all these types of metastability, which we have just listed, in a more general context. So, and therefore, so our view from a dynamic systems point of view on metastability would be that we are talking here about long but transient regimes of dynamics. So regimes of dynamics means this dynamics can be of different behavior. So when we compare it, so to say, with the so with a deterministic view, I will do that so to say in a moment. But for the moment, we're not even thinking about attractors or whatever. We're just thinking about that we are talking about different regions in state space. So we have a dynamics which happens in a region in state space, and these are called the almost invariant states. So this would be a metastable regime, then it occurs in an almost invariant region. So what means almost invariant? Yesterday in the hands-on session, so when we were talking about bifurcations, I pointed out very clearly what is an invariant set. An invariant set is, so to say, which when you think about the model system, it's always mapped onto itself. If you are sitting once in this invariant set, you stay there forever. And so here, this is not the case. So because in a metastable regime, you stay only for a certain while. So there is a time interval, long-lived, but it's transient. So, and after this transient, and this can be arbitrarily long, so to say, and changing in duration, you go somewhere else. So let's have a look at this sketch. So because this type of behavior, that you go there and you stay there for a while, and then you go somewhere else, has to be realized, so to say, by mechanisms where you have to this region, which is now the yellow one. So you define basically a region and state space, so in which the trajectory stays with very high probability for a longer time when it arrives there. So therefore, so you see this kind of long trajectory moving in this area, which is yellow here, but then there are attracting and repelling tendencies. So when we are thinking about deterministic systems, so we were already talking about stable and unstable directions. So along the stable direction, you reach, so to say, a settle point, and along its unstable direction, you leave. And this is more or less the extension of this kind of concept. But of course, you cannot talk about manifolds here because we are not in a deterministic setting. So this is just a trajectory, but it is attracted somehow to this region, stays there for a while, and then, so to say, it's ejected along the repelling regions. So this two type of tendencies have to be combined. They have to coexist in the neighborhood of this region and state space where, so to say, metastable regime, so to say, takes place. So this is the basic setting we have in mind when we talk about metastability. Now, let me give you an example. And we look now at a bistable system, which is subject to noise. So we have seen bistable systems in this. So you see this yellow dot. So now it's jumping to the other well, so to the green, and then it's jumping back, and so on. So we have already in the last week talked about bistability a lot, and this is now a manifestation of it. What we see is when we have a bistable system, it is subject to noise, then you would see this type of behavior. And this would, of course, fit very well to the concept I just explained, because now you can think about, so to say, a region which is in the well, but it's not only, so to say, the stable fixed point, which is at the bottom of the well, but it's a larger region, because it has to be a larger region, because the noise will make the trajectory wobbling, so to say, in each of these wells for a while, as you see here. And then, of course, so to say, this type of dynamics would be one example of a metastable system. And this, of course, applies not only for bistable systems, but it applies to any multistable system. You would immediately, so to say, see that in a certain noise range, you would see this type of metastable behavior. So your attractors, which have been there in the deterministic system, are all metastable because the noise will kick the trajectory with probability 1, depending on the noise strength, how fast this goes, out of your potential wells. So this is what you have to expect. Okay, now let's point out the differences between multi-stability and metastability. Because this is very important. So this discussion, there is some confusion in the literature whether, for instance, this example which I just presented, the noisy bistable system is metastable or is not metastable. So let's compare the two. We take again this example. We have this double bell potential, and we compare the deterministic view on the left and the stochastic view on the right. So what happens is in the deterministic view, of course, so we have stable states. These are just in the bottom of the wells, and there are basins of attraction, and that means initial conditions which start in the basin of attraction will go to either one or the other stable state and stay there forever. So this would be the deterministic view. But when we have noise on the system, this is not going to happen, as we have just seen in the simulation. So there is a little devil, so to say, sitting on my ball, and it's kicking it all the time. And therefore, so to say, it would not stay in the well, but there is a path which gets, so to say, the ball out of the valley and kicks it over the hill into this other state. Okay, so then now we can, so to say, have our in green and in purple defined regions, which depend also maybe on the noise strength in their size, to make it identifiable that we are in one state or we are in another state, but then there are transitions between them. So why it's only for a range of noise levels? So this is another example. So this is a highly multi-stable system. It has 150, if I remember correctly, something like that, attractors. These are all the stars over there on the left side. So all the stars are the attractors. So then all the black dots are points in the basin of attraction of the attractor in limit. And then I have put here also a zoom in. And so then you see that the middle attractor has this huge basin of attraction where we have, so to say, all initial conditions converge. Then there are two period 3 orbits around them in red and in blue with their basins of attraction. And then there is a complete mixture in principle, what's in the background. And we put noise on it. What we get is a probability distribution over the state space. So this is shown in the last figure. So for different noise strengths. And as we, so to say, increase the noise strength, we realize that we won't see, so to say, all these type of patterns which are appearing basically in this hopping between the different attractors. So because now we have not only two as in the bistable system, but we are jumping between different states. But if we increase the noise even further, what we see is practically a diffusion in state space. We would not be able to distinguish different states, and therefore metastability would not occur anymore because we are not able to distinguish it basically from a diffusion which includes the whole state space. So therefore, we see this type of metastability in noisy multi-stable systems only for certain noise strength and certain interval. Now let me come to mechanisms of metastability from, again, the dynamical systems point of view. So we have here different examples, and I will go into more detail for all of these examples, but let's have a look first, so to say, at the overview and then go into detail how here for all the different examples, which are mechanisms, how metastability in and nonlinear dynamical systems can occur, so how this really happens. So the noisy bistable system we have already seen. So this is there on the left side. Then we will talk about stable heteroclinic cycles. We will look at different crisis phenomena. So there is only one shown here. So this is the attractor merging crisis, which we see here in this kind of overview. Then we have intermittency phenomena. There's also only one example which could happen, and then we talk about chaotic cells. Now let's go through these mechanisms and understand how really metastability occurs. Let's start with the heteroclinic cycle. So what is a heteroclinic cycle? So it's occurring in nonlinear dynamical systems which have different, in the deterministic case now, so to say, so just to explain what the background is, so it has different stable solutions. So usually people have their either fixed points or periodic solutions, both as possible, but these are located in different parts of the state space. In this example, so we have basically 3 of them, and we now, so to say, let this system run and see what's happening. So you see this ball, the yellow ball is moving between the different states. It's jumping between the red, now it's in the green, now it goes to the purple, now it's there. And then finally it jumps back to the red. So we can run it again so that you can watch it. But what is the underlying structure? Is so that there are connections. There are connections between the red, the green, and the purple point. So these are, in the deterministic case, so to say, the stable manifolds. Of course, we cannot, when we are observing, so to say, something in nature, we would not see definitely, so to say, this behavior, because in nature noise is inevitable anyway. So, but you would still see, so to say, this jumping between different states, and it's more or less regular because it's really going from one state to another. But what you also see that the time, so you dwell in the neighborhood of one of these states, might vary. So this is not something which has to be always the same. So because you are approaching this type of loop dynamics, so because you are going always around, but you're not going around in a regular manner. It is a cycle, but the closer you come to this loop structure, then the longer you stay in the neighborhood of that one of these states. So this would be one of the mechanisms, so which we can discuss. And now we come to the attractor merging crisis. So this is a bifurcation, which is a global bifurcation. So in the last week, we were talking only about local bifurcations, where you can think about eigenvalues, so which make the system, so to say, unstable, so or the state in which you are, and you can identify the different transitions from stability to instability just by eigenvalues. This is impossible when you have global bifurcations. In a global bifurcation, usually different sets in state space are interacting. So in an attractor merging crisis, for instance, so this is a collision of 2 different attractors, but there is a mediating orbit. So there's an unstable periodic orbit in between, which is, so to say, the mediator over which this transition happens. So this is a kind of door through which the trajectory can go from one part of the attractor to the other part of the attractor, because now we would have, so to say, 2 parts which are connected, but they are connected via this unstable periodic orbit. So it's very nicely seen in the band merging crisis, which is a special case of the attractor merging crisis on the right. So I have drawn the bifurcation diagram of the logistic map, which probably everybody here knows. Who has ever studied a little bit chaos theory, I put something into this picture, and these are the red and the green dashed lines. So because these are the unstable periodic orbits. So when you have a period doubling, so for instance, the one to the left where the red dashed line starts, so the periodic orbit loses stability, continues at the red dashed line, and then, so to say, the period doubled solution occurs. Now, when we continue this line and follow it, so then we see that at some point, far in the bifurcation diagram, so there where we have two branches of chaotic chaotic attractors, so to say, so two branches which are first disconnected, but then they merge. And this is the point so where the red dashed line meets the attractors. And this is then, so to say, the bridge over which the trajectory can jump arbitrarily between the two branches. And we have infinitely many such attractor merging crises. So the second I have also depicted with the green dashed lines. So it's another periodic orbit, and there are four different parts of the attractor merged to two. So you have lots of those. So all of this leads to crisis-induced intermittency, and this gives you what's shown in the middle. So because now you see the irregular, so to say, movement of the trajectory between two attractors, so which are in fact one, but the trajectory spends in one part of the attractor a while, then it goes to the other part, spends another while, and we see that this is a completely irregular process. So this is something which is not periodic or whatever. So this would also fit our definition of metastability. So this could be a mechanism how this occurs. So we have another one, is another crisis. This is the interior crisis. What happens in an interior crisis? It's also a global bifurcation. And so that means we have here an attractor, which is the one on the left side, far left. And what? Yeah.
I have a question
Sorry.
about the previous example.
Yeah.
Is it possible for this structure to split again after some time? Because in the logistic map, you get, again, after some time, you will get just one trajectory, right? After some time.
Wait a second. So here? No.
Yeah. I mean, after.
No, this is one trajectory. So what is so I mean, I don't understand the question.
Yeah, I mean.
Maybe you rephrase it.
Yeah, you're having this convergence, right? Is it possible to have?
They are coming here, yes.
Is it possible to have this separation again?
Yeah, of course, because you only need to change the parameters, so to say, that you go either in one direction so that the attractors merge, but you can have, of course, the opposite case also when you reverse the directional parameter change, then they split. Yeah, you can have that as well.
But if you don't change the direction of the parameter,
No, that you cannot.
you cannot.
No. Once the crisis has occurred, and so you don't go back, then you would not see it, but there could be, of course, so to say, far away, another bifurcation, another crisis which could occur where they split, but which is also very independent from the first one. This can happen. So, okay, now we are here. So we have on the left side, we have one attractor. So this is before the crisis, interior crisis. And so after the interior crisis, we see the picture in the middle. So this is the Ikeda map. I forgot to put it here. And so what happens in this case is, again, mediated by an unstable periodic orbit. The attractor collides with a chaotic saddle. Means we have again a chaotic set, but this is not an attractor. It's a chaotic saddle, it's an unstable set. And then this unstable set is incorporated in the attractor. So practically, so to say, the former small attractor is basically absorbing the big chaotic saddle into it. And so therefore you see then this huge chaotic attractor And an interior crisis, when you look into, say, the dynamics of a system, is always related to a sudden increase of the size. So your attractor is exploding, basically, in this bifurcation. And this is what you would get after the interior crisis. You see again, so to say, that so you stay most of the time on the previous attractor, but then there are some periodic bursts, you see, so which are, so to say, interspersed in the time series, where you have the trajectory which escapes to the chaotic center, moves there for a while, gets back. Everything again mediated by a periodic orbit, unstable periodic orbit, which would be, so to say, again, the mediator of this, so to say, switching between the small attractor and the large attractor. Again, you can see this also in the logistic map. Therefore, I put again, so because many people are familiar with this, you see exactly this transition. So in the logistic map, in the bifurcation diagram, in any of the periodic windows, I've depicted only here the period 3 window, so what we have, and then the interior crisis is what you would see here on this side. On this side, this is the interior crisis. So you see the small attractor here. Now this attractor collides with the unstable periodic orbit, which appears in the saddle node bifurcation of periodic orbits when the window opens. It goes further here, it's a period 3 periodic orbit, it's unstable and it collides with the 3-piece chaotic attractor. But here, in between, so you see chaos here, and this chaos, when this periodic orbit appears, is of course not gone. The chaos is still there as an unstable set. It's sitting, so to say, in the state space, waiting, so making the transients very long. And you would see that they are then incorporated in the interior crisis. So the interior crisis, again, so to say, makes it possible because the trajectory can tunnel now through this unstable orbit into the state space, and therefore, so this part here is also incorporated. And what you see is, again, this intermittent behavior. So, and that means we would have two different distinct dynamics, because we would either dwell on this little set, which was the former stable one, or we would dwell on the large set, so with perhaps very different properties. So again, crisis-induced intermittency, so which is behind the whole story. So let's see that again as a movie. So we see again our yellow ball jumping on the small set. And from time to time, so we will see it pronounced here. So this takes a while. So now it's getting to the next little span of jumping out. But here we will have a larger one. We will wait for that one. And then I think, so we have seen it. So what is really going on here? Now we are approaching it. So we see one jumps a little bit outside, but now we should see so that our yellow ball hops on this purple part of the attractor outside, and is now in a completely different part of the state space, and then it comes back. So now we are again back on the green part on basically forever. So this would be also a crisis-induced intermittency after an interior crisis.
Please.
So, yeah, please.
What kind of physical systems could behave like this?
Sorry?
What kind of physical system could behave like this?
A physical system which has a period doubling cascade to chaos, any, because all of them, unless you have this very particular systems which are called hyperbolic chaos, they don't have periodic windows, but any other, so which has a period doubling cascade, you would see that. You would also see it, I never checked it, but so I would bet when you have a period adding cascade, because there you have also periodic windows, so to say, together with mixed mode oscillation. So you have, so to say, in the bifurcation diagram, so you need going through between mixed mode oscillations and chaotic regimes. So there you should also see the same thing. So these are large classes of systems. So any oscillator or whatever is doing the job, so to say. So this would be another type of dynamics, and this is type 1 intermittency. So now we have also again a dynamics which switches between almost periodic behavior or principal periodic behavior, so very close to it, and some chaotic stretches like here. So this is in the Lorentz system, and this is the periodic stretch. This is the other one. We can also run this. So where is my mouse? No, so so something is not working here. So okay, I probably made it wrong. Wait, no, this is not what I wanted to do. This is even not my screen. Here is my screen. Ah, yes. Now, okay, so we see it also running periodically on this purple periodic orbit. So then it goes to all the green area. So just a moment now. So we are going here on the periodic, on the chaotic part, and then we go back to the periodic orbit. We would see it here. So now we are again on the periodic orbit. Okay, so now, again, the same thing happens in a large class of systems, because again, it's in the periodic window. So this was the picture we just saw a minute ago. Period 3 window. We were talking about this transition. We are talking about this transition. So because when the window is opening, and so we go with our parameter in this direction shortly after. So we are in the chaotic region. So this is the intermittency transition to chaos. We see that the trajectory would, and you can see it here also. So the more black the points are, so to say, the higher is the probability that the trajectory is there. That means in this 3D, so to say, areas in state space, so we would have a high probability that the trajectory is there. And that means these are close to this former periodic orbit. The periodic orbit itself is not there anymore. So because we are already in the chaos case, but so we see these remnants of the periodic orbits, which are also called ghosts of the periodic orbit when you are beyond the center-node bifurcation. So the orbit itself in the deterministic sense is not there anymore, but we see these ghosts, and therefore, so to say, we have again, so to say, a metastability here. Another crisis is a boundary crisis. So where we would have, chaotic saddle, so on which the trajectory would dwell, and the chaotic saddle comes, so to say, into play when the attractor collides with its boundary. The boundary here is this axis in the logistic map, so we have also a boundary crisis. So here there's an unstable periodic orbit, which is not visible, so it's the 0, and then we have the chaotic attractor, and it hits basically this periodic orbit, which is the basic boundary, and then here this chaotic attractor disappears in quotation marks, because you don't see it as an attractor anymore, but you see it again as a cell. And this is in the Ikeda map, which we had seen already before, and we can also let it run. And so we can look again at our yellow ball. So how it dwells on the chaotic saddle for a while, and then finally it basically jumps off and goes, in this case, to a fixed point in this map. Here, so to say, we would not see, this is the only example which I have shown now, we would not see that this is repeatable. So, but we had included that also in our metastability. Is not necessarily so that it's repeated, so this type of transition. So what we get, so this would be an example for this. So finally, we come back to these mechanisms, so to this overview. So I have shown you lots of different possibilities how metastability can be manifested in systems. So there are different mechanisms behind. And we can, of course, also look at statistical properties. We can look at so the PDFs, so the probability distributions of the times which you would dwell on the different states. So, and we see, so to say, that most of them are here. So this is a logarithmic scale for the ones which cannot see that from the back. Sometimes we have a linear scale here. So sometimes it's exponential, sometimes it's a power law. Mainly it's a power law. So what we see, so because this is like a random process. So you have a random behavior. So how you really dwell, or how long you dwell in certain states, and therefore you get for these durations, of course, a probability distribution which tells you that this is practically a random process, and this is what you see. So now take the rest of my time to go on the last example. So on the chaotic setup. But now we would like to see, so to say, that this cannot only be, so to say, as we have it here, beyond the boundary crisis, but it can have a much more interesting behavior because you can get a switching between very different spatial patterns in neuronal tissue. And this is what I would like to tell you. But before, so this was just an advertisement for your talk, but nevertheless, maybe in the next session as well. So because, well, of course, I have not discussed at all is how to identify these almost invariant regions. So there are, of course, methods on the market, but it's not too much. So Klaus has, of course, already mentioned a lot in his talk. But we can, besides that, so to say, also look at hidden Markov models, for instance, by partitioning the state space to see what the trajectory is doing, or so what people do to get this EEG micro states, which I showed in the very beginning. So to say, they try to identify these patterns really, so to say, so in real EEG scalar potentials. We can use Verwolf exponents, as I will show in the next example. So to do so, or we can use recurrence plots. So there are lots of methods, so to say, on the market, even though with all the problems Klaus discussed. So this is an open field, I would say, because so all of this, so also all the mechanisms are now explained in terms of what we know from dynamical systems theory, but this is upon models. So we are based on models now. What we finally see in nature, this is a different question. So now before we go to this chaotic center, which I would like to show you, so that we have really different patterns, so which are united. let me give you some ideas so which we would need to understand this chaotic sample. So this is how basically my collaboration with Carol started. So we were looking at extreme events in two different systems. So in hyper-eigenblues, because I'm in an environmental institute, and epileptic seizures. What do they have in common? This is the first question. And they have in common that mathematically, they can be described with the same type of system class. And this is excitable systems. And what we define as an extreme event is far away from what people in statistics would do. In statistics, so what you define as an extreme event is some event which is, say, for some observables larger than a certain percentage, so to say, of the whole, so that it's in the tail, say, of the distribution function, so that it's larger than a certain fraction. No, we were looking at this from a completely different point of view because we were interested in mechanisms, how this occurred. And then, so to say, we defined it as follows. So we have a usual behavior, which is all the time there. And something unusual is happening. So it's also here depicted by a large P, but this unusual thing can be also something different. Now, what is an excitable system? I would like to remind you, most of you will probably know this, that these are types of systems which have, so to say, an activator variable and an inhibitor, so that the activator is developing a large spike like in the neuron, and the inhibitor so would produce on a much smaller time scale, so a smaller time scale would also grow, but then finally is strong enough to inhibit the growth of the activator, and so therefore this type of dynamics in the excitable system goes down and goes basically back to some state which in a neuron would be, or in a simple neuron model, would be a kind of resting state. So, okay, so knowing this, so we look once again, and we have seen this model already. So in the last week, and we see that the null points are basically the same. So except for for the angle of the second null point, they are looking very similar. One can describe, so to say, excitability in part of excitable tissue, and this one would describe hyper-eigenblues here in this case in New Zealand. Okay, so now let's look at coupled Fitzhugh-Nagumo models. So these are the ones which you look at in the brain, for instance. And so we couple them. So these are the equations, and then we couple them with a certain topology. And so I will tell you in a moment what topology we use. But what we also use is that we have a local environment, so to say, about each of these Fitzhugh-Nagumo models. So where we have a certain coupling radius, where we have lots of couplings, so that we have something like a local coupling. So these are heterogeneous networks. So we have looked at heterogeneous networks. So that means they have not the identical parameters. So the parameter B here, so which also determines the frequency of the oscillation, so would be distributed in a certain interval. Now let us look at the dynamics. So for two current systems. So what do we observe? We observe for certain coupling strength cycling, which is a chaotic oscillation basically, but with a very small amplitude. But then we have another coupling strength here, and we see something completely different, because now we see that there are these huge excursions in state space. And these huge excursions in state space we call extreme events. And they are what I described, so to say before. The usual behavior is the small oscillation, but then there is one extreme event once in a while, and which, so to say, has a much higher amplitude, and it is self-generated, but it's also self-terminated. And so this is the inter-event distribution we get here, so to say, again, so something which looks like a random process. Okay, but we are interested in the mechanism. So what is the mechanism? Why do we see these extreme events? So what is behind? Let's have a look at this process just only for the two coupled physical systems. And let's take one of these extreme events out and analyze it. Just a zoom in here. So what we see, and we see now the two excitatory variables, so the activator, and then we see that the root one, so to say, which is x2 in this case, is going off. So it's not continuing with this oscillation which we had before. And then, so to say, the black one tries to go back as usual, but then it is taken by the red one, and they both together form this extreme event. So that means we have this, behavior. One is initiating, so to say, to form this event. The other one is taken and just pulled with it. And when we look at the mechanism, how it works, so then we see that now we have, so to say, a close-up view in the state space. So where we have a fixed point there, so there's that point, but this is not the important ingredient to get this extreme event, because we have a chaotic behavior here, so which is this small oscillation. But then, so when we look how this large oscillation occurs, then we realize that there is this type of channel forming. There's a channel in state space through which the trajectory has to go to form an extreme event. So because these are all the points, so to say, plotted, which are before an extreme event happens, and they are all lying in this channel. And so that means this is a characteristics of this type of formation of extreme events, that there are these channel-like structures. And since it's chaotic, so it's like a tube. So, and this tube, so to say, has a hole, and the trajectory has to go through this hole to make this excursion. And therefore, we need chaos, because chaos makes it rare, because the hole is small, but it is recurrent. So the trajectory will always, with probability 1, basically, find from time to time this channel. Of course, the size of this channel determines the interspline intervals. So how often do we have such an extreme event? But it will always hit this hole, go through, and make an extreme event. So this looks like this type of machine you see there. So to say, you really need, so to say, the right channel to get this thing winning here. The extreme events here, they look the same way, so to say, as these machines are working. Now let's look at a network. So in a network, we would see the same thing. You see, this is a network of oscillators now. And so we look now at the dynamics in this network. It's fully connected, as we see. And so I would like to show you so that this type of dynamics, where we have here this small amplitude oscillations, and then these extreme events which are embedded, follow the same type of mechanism, which we have just seen in the um, slide here for the two couple, but now we have to go to another. Now we have to go probably to, this is a desktop. Let's see whether we can do this. Over here. Share this, what do we see? Okay, yeah. So this is what we see. So do we see something? Yeah, it runs. Okay, so this is the excitatory variable on the top, inhibitory here, and so this is basically what is the connection between them. And now we see, so to say, that we have here the dynamics. So of the which is basically the mean value of the whole network, and you see now you have seen that some oscillators here have made a huge excursion, but the others didn't react. So therefore, this excursion was basically damped out again. So, and now we are approaching this huge event, and now look what's happening, because now we are going to see that a part of these oscillators are making the excursion, but then they pull basically after a while, they pull all the others with them. So now you would see them going up, okay? And now everybody else is following. And so therefore we get, so to say, this extreme event in the same manner as we have learned it from the two coupled oscillators in this type of network, fully connected. So what we see here in this movie. So we are not going further in this detail, but go back to our presentation. So here. So this is the same type of mechanism which we have seen. So now let's change the topology. So we have a fully connected network. Now we want to change the topology. It's exactly the same type of movement. So, but now we are changing it in such a way, so to say that we start with the grid, but then with a certain probability, we introduce long-range connections. So that means we are producing now from this regular grid, a grid, or say a network. So it's not a grid, so just by, so the grid happens that we can really show it in a nice way on the screen. But what we have is a small world network. So that means we have mainly, we have local connections in this local neighborhood, but still, so to say, we have some long-range connections. So if we do so, we see, and we go to another video, something else. So you have in principle seen that already. So in the talk of Klaus, what did we do here? Yes, and here. We are going to this one. So Klaus has shown that already in his previous talk, not today. So now, so just for visibility is again on the square. But what you see, there are waves. So everybody who has had some contact, so with patterns in nonlinear dynamical systems in space, would have seen these type of patterns. So because there are waves which are, so to say, going through the state space, but then when they meet each other, they annihilate each other. So this is the nonlinear wave formation, and this is what we would see. So this is one of the patterns we see. But now we see here, so this is again the mean value. So, and now we see here basically something happening. So there's something going on. So, and so now it becomes a little bit more irregular for a very short while, but then we go back to our waves. So, and we speed up a little bit the process. So, and let me go a little bit further. So because we will see now in a moment, I was not shifting the whole thing too much, but let's wait. So because now I can explain what you should watch. So now we see there is another transition coming up. So here we have these waves. Now we see that our time series looks completely different. So we have another transition here, and transition to an extreme event here. And now watch what is going to happen. So here we have still our waves, which are just propagating through our state space, and so on the network, and now it's happening. Oh, no waves anymore. And what you should see is that there are excitations popping up, so to say, here and there on the network. So you see them, once here a little bit, once there a little bit. And now, so when we approach here, so a huge part of the network will be excited. So which was an extreme event in our understanding. Then we see a little bit of waves again. Then we go back to this low amplitude oscillations. Here and there is something going on. So, and now you see already what's going to happen. There is another extreme event coming. So we are jumping up. So there is a flash going through the whole network. And then we are back to our low amplitude oscillation, so that here and there is something coming up. And I think here we should go back, so to say, to the wave patterns. But so you have seen what is the idea about. So there we have now different patterns. We have waves, we have low amplitude oscillations, and we have extreme events. There are three different patterns, distinct patterns, which are happening in this system, and each of them, so to say, can jump to the other. So because we have transitions from waves to extreme events, we have transitions from low amplitude oscillations to extreme events. Now we came from low amplitude oscillations into the waves. And so all these transitions are present. And this goes on practically forever, at least until the time we stopped the simulation. So therefore, we cannot say that it is forever, but these transients are extremely long. So now we go back here. So what we saw are three different patterns. So the low amplitude oscillations. So this is in state space basically only what is this kind of oscillation here in this corner. Then we have traveling waves. So then these are this green dots here. So this is a close-up view, so that because it's not really distinguishable. But then we have also these global oscillations. So we have this huge excursion in the state space. So these different attractors we have in the system. So we are completely deterministic. So there's no noise here. So we have no noise-induced transitions in this system. It's purely deterministic, but we see this kind of changes of different patterns. And now we look closely to the time series and see once again what we already saw in the video. So now we color-coded what is wave, what is low amplitude oscillations and what is extreme event. And we see, so to say, that there are transitions for a very, very long time. So between these three patterns, the waves, then the small amplitude oscillations here. So because you don't even see, so to say, that there are these kind of excitations locally, and this will be an extreme event where most of the network is really defined. And now we can have a look, so to say, how to characterize, because we have to find an automatic. And this is what I said, we need to distinguish the different patterns. So how can we do this? And this is shown here. So with different quantities, of course, this is the time series we saw for our mean value of the excitatory variable. Then the second one is the number of oscillators which are firing, which is of course highest in the extreme event. But we see also the last one. For the last one, we took the instantaneous Lyapunov exponent and see very different patterns. So the green ones are the waves, the blue ones are the low amplitude oscillations, and the red ones are the excitations for the whole tissue. So you see, one has to invent for each of the systems criteria how we can identify in which state you are. Because otherwise, how would you like to analyze long time series if you don't have any criteria how to distinguish these patterns? And these are the ones here. So we came up with some ideas. So how to do this? This is, of course, specific to this system. So to distinguish between the different regimes we are in this metastable process, because this is pure metastability. We have three different regimes. The trajectory varies on these regimes for different times. And we have, of course, to identify now which pattern is which in such a time series. And so these are the criteria. So of course, extreme events have to be larger than a certain threshold. Then for the waves, at least one of the units should be excited, basically in a time interval, but there are no events. And the low amplitude oscillations are neither events or waves. So one can do this, and one can also look at the distributions now of the switching times, the wait times between the different patterns, but also their duration. And again, we see that this is a random process. Now, let us look, so where we find this. How robust is this kind of switching? Is it just by chance? Just finding, oh, this is one parameter where it works, and that's all. No. So this is now this rewiring probability. So how many long-range connections do I have? And so then here we go to different attractors. Here the attractor is low amplitude oscillation. Here it's traveling waves. Here it's global oscillations. But the whole yellow area is basically this chaotic channel, what we have here. So because we have this hopping between different patterns, but you see, so to say, so there is always either here or there, so to say, a small number of simulations which go to an attractor. So that means there is an attractor here. So for most of these parameter values, but most of the time we end up in our simulation time, which was very long, only with the transients. And in nature, you would see the transients only. So, I mean, you would never get to the attractor. So this is quite robust. So in terms of revival probability, but also in terms of the heterogeneity which we had. Because we had the heterogeneity in our oscillators, our Philips-Laguerre oscillators, and we varied that as well, and see also large areas. So where we have even parameter values here, where we never into an attractor. Okay, so this is of course the simulation time. So we would probably end up with an attractor, but so then we would have to increase the integration time for very, very much, very long time. Okay, so now we have seen this pattern switching, and we could identify the method how to distinguish between the different patterns. So this is one of the ingredients you really need to identify metastability. So you have really to fix criteria to get an identification of your patterns. That we saw that, so to say, we have exponentially distributed durations for the patterns when we and for waiting times, and we saw this for very large parameter intervals. So this is how it would look like in the state space of the mean values. So you see, so to say, in blue, basically the area for the low amplitude oscillations, in green, basically the waves, and in red, the extreme events. And now we want to have a look at the transitions, because what is important in this whole business of metastability is, of course, not only to identify that the system jumps between different regimes, but also how does it do it? So let's have a look with the same color coding on this kind of transition. And here are now shown, so to say, the transitions either coming out of the low amplitude oscillations, going to waves or extreme events, coming out of the waves, going to low amplitude oscillations and extreme events. And this is extreme events to either going to low amplitude oscillations and waves. And we see that these are, except maybe for those, so this is not so clear, but for those it is very clear, there are very narrow channel-like structures through which you go in state space. So you have to hit the channel, which we have seen already for the two coupled systems. So where we saw that there is a certain route in state space through which you have to go. And this is what we find here in the network as well, so that there are narrow channels, so for which you can go and see, so to say, this jumping between different states. And now let's have a look, so to say, how these transitions are governed. So what governs whether you go from one to another? This is a sketch, of course, but what is important here is this center point, which was in the middle of this rotating, this rotating trajectory, which is here in the corner. So we have here the wave structures, we have in red the extreme events, and we have the low amplitude oscillations here. So this is again mean values of our two variables. What we see, but what we would like to understand is how does it switch? So because we switch here into extreme events from the waves and from the low amplitude oscillations, we come in here from extreme events going to either waves or to low amplitude oscillations. And we would like to have a closer view now. So what's really going on here? And now we see that the stable manifold, for instance here, so of the center point is determining the whole business. So these manifolds, which are now the ones of this center point, there's only one point which basically determines the whole thing, not only one point. So because we see also the switching when you come out of the channel, either going to extreme events or to waves. But so these manifolds and these fixed points, the unstable solutions, as I already pointed out in my previous lectures, are deciding what is going on. So we see this very clearly when we come from extreme events to waves. We go on one side of the stable manifold. If we go to low amplitude oscillations, we go on the other side. So that means there are structures in state space which make it possible, so to say, to understand this type of behavior. So what type of dynamics would we have? So, and finally, so to say, this is very general. So that we have patterns in nature which form spontaneously, and that we have transitions between them. This is not something which is confined to neuroscience. So we have lots of other patterns as well. So these are nice figures, so to say, from Flavio Fenton's website, who is working on cardiac behavior. So where you also have nice waves on one hand, or you have something very irregular, which is basically the so already an indicator that sudden cardiac death can happen. So this would be the normal situation. The other one is more a disease. So it's also changing from one pattern to another. So what we have seen is that these transitions, so to say, these switching patterns can have very different nature, which all would be able to help understanding transitions which are observed in neuroscience and in many other fields. So we have seen heteroclinic orbits. What I have not talked about is adaptation to external signals, but this, of course, can also happen here. I was only focusing on mechanisms which are self-generated, because an external signal you just plug in and then something is happening. Then we have noise-induced pattern switching, of course. And what I showed here in more detail is really a pattern switching which is purely deterministic. So it can last for a very long time, and it's mediated by a chaotic cell. All these kind of patterns are comprised in a complex structure in state space, and you go basically from one structure to another, and this goes via these transition channels. And this is also something I would like to emphasize here, because this is not the only case in this metastability business, so to say, where you have this type of transition channels. Look at any noise-induced transition, then, so what people are looking at and can compute are the so-called most probable exit paths. And these are exit paths in state space, so over which the trajectory with highest probability would go. And this is also a kind of channel-like structure, what you see. So because the probability to go through this trajectory, which is almost deterministic, is much higher than the probability to go somewhere else. So if you would plot a probability distribution for all the trajectories which go from one state to another due to the noise, you would see that this almost deterministic trajectory has the highest probability, and the other probabilities go exponentially to zero. So you would not see this. So that means this seems to be, at least for these two examples, the way how it might work. I don't claim that this is always the case, not at all, because we don't know. I know it, of course, also for the crisis phenomena which we have discussed previously. In the crisis phenomena, the mediating unstable periodic orbit is also the door. So that means the trajectory has to go over this unstable periodic orbit to reach the other part of the chaotic attractor, either in an interior crisis or in a attractor merging crisis. So there we see the same phenomena. So this points to the fact that these kind of channels, one has to identify. They might be there in many cases even though we cannot claim anything about, say, this is always the case. I'm far away from saying this, but so this would be a possibility that identifying this type of channels would also help, maybe even prevent certain transitions. Because this would be, of course, also something wanted if there are some dynamical patterns you don't want, they are undesired, then you have to think about strategies to design, so to say, a kind of control, so to prevent those. And if this type of transitions would be associated with such transition channels, then it's much easier to concentrate on those to find a prevention than looking at the whole state space and we have no idea. So where are the transitions going on? So, but this is for the future. Thank you very much for the any questions? Yeah.
I think it's more of a general question because we were been discussing the idea of criticality of the brain, and like most metastable states, they are close to a critical transition. Do you think this relates to function in any way, considering a metastable system?
This is a very interesting question. So, and I'm thinking about whether this could be, so to say, true, but I would say it's too early really to say something definite about this. So it seems like this, that we are for many of the transitions really close to some bifurcations also. So because all these crises, we are in the neighborhood basically of these transitions. So then we have the ghost solutions, which are also basically close to a bifurcation, but this seems not to be all the time the case. So therefore, I would say there is a potential, so that this is indeed the case, but probably not for all transitions, so which lead to metastability. But there seems to be a close relation which needs to be studied much more in detail. And I'm already thinking about it to go in this direction, also to look whether this type of idea, so that you have to be close to criticality, so which I would translate for me at least, that you are close to some bifurcations, so which are happening. This could be the case, but I would not say that this is always the case. So we know too little at the moment, I would say, whether this is always so. But there are indications that this could be the case, yes. Yeah.
You happen to know any works on metastability on ecosystems?
On ecosystems, no, except for the fact that we are working on it. But there are no results yet.
Yeah.
So because these are partial differentiation usually, and we are working on pattern switching there. And you can see it. So this is what I can tell you, but it's on very long time scales.
Yeah.
And so most of them are basically rate-induced transitions. So I would not even say that so that this would be metastability as I discussed it here. So because usually we are not changing parameters, but so in these type of transitions where you see pattern switching in ecosystems, you change usually a parameter. And that is not exactly the same. Yeah.
Ulrike, thanks. It's a very nice presentation of these different metastability methods. My question is, when you relate this now to something to like brain dynamics or something, in order, the question is, what really applies that something,
Yeah.
does something when you know, I mean, we don't have to pretend we know nothing about the brain, right? So if we know, for instance, that we have one parameter that we could potentially tune to go through such, so if wouldn't that correspond to something to like co-dimension one bifurcation? My question is, would this reduce the options that you see? Would this help you in figuring out this can be a potential mechanism? This is likely that not a potential mechanism. So this is my first question. And my second question would be this noise-induced tipping that you described. I feel personally, and you explained this nicely with this appropriate regime of noise that you need, right? Otherwise, if the noise is too big, you will not see it. So there needs to be. So I feel like this is a bit of a confusing in the community, confusion in the community, because obviously it's still a bifurcation that's underlying it. It's just not visible if the noise is too big, and you jump obviously, but you can still have this bifurcation. So maybe you can comment on this between these two things.
Yeah, okay, so I'll start with the last one. So you cannot see these bifurcations anymore. So when the noise is too large, you see really a diffusion in state space, and you would not be able to even identify, so to say, different patterns. You would not even see that there is a definite transition from one pattern to another, because the whole system would go over the state space just randomly, like a diffusion process. So that means even though there was deterministically some bifurcation structure or some structure in state space, so with cells, with phasal boundaries and so on, there you would not see anything of this.
Let me put it then the other way. Let's say, coming back to Klaus's talk this morning, so he shows there's no signs of critical slowing down before a seizure, right? With all these mechanisms.
Yeah.
My point is, could you still exclude this? Because you could simply be, that at that range, it's noise-induced tipping and you don't see it. But still, if you, would have this one parameter that you can move away for away, then you still have the bifurcation, right? But it's simply that if you're right there and you have just noise, then you don't see it, right?
So in these noise-induced transitions, you usually don't change a parameter. So this is just a fixed stability landscape, and you just put noise.
Exactly.
So that means, these noise-induced transitions, they basically assume that there are different patterns. So, and if you cannot identify these patterns any further because the noise is too large, then you would not even see everything what's below the noise level, so to say, because it's not visible anymore. And the noise-induced transitions, as I mentioned, just in the last part, they also have these kind of channel structures, because there is this most probable exit path. And when the noise is too large, you cannot get this any further, because so then your probability distribution is basically a distribution which is equal in the whole state space. So then this type of property that you have a transition between distinct areas of the state space, this is lost. So you would not see that any further. So the first question, can you repeat?
It's like co-dimension one and it's all different mechanisms,
Yeah, so you can do this. So to get from observations to mechanisms, just by trying to probe to think about how the dynamics you are observing, so to say, manifests maybe one or another transition. So you can do it with exclusion. And when we looked at these homoclinic bifurcations in thermosensitive neurons, this was exactly the case. So because we saw experiments and there was some observation. And then, so to say, from the observations, just looking at the time series, what they do, one can formulate hypotheses, which one can check finally to see whether this or that transition could be the case. So that means if you know enough about these kind of mechanisms and what are their characteristics to distinguish them, you can also go back to the experiments and try to figure out which one it is in the best case. Whether this is always the case, I don't know, of course. But so this example showed me at least, so it is possible from certain behaviors to come up with ideas what type of metastable transition this could be. But so looking at the time series alone usually doesn't help. So
I think this could be a really cool avenue, you know, to say, okay, you can distinguish from this, and if you have the option to perturb the system in a way, then you should see some
something else. Yeah,
in this system, but not in this.
This is what one can do. So because all these behaviors are really confined to certain situations, and if you go away from it, you would not see it any further. So therefore, you could, if you can change your parameters, you can basically try out different mechanisms, and compare with what you observe. So this could be an option. Yeah. Yeah.
Do you think that, I mean, because I was thinking about like real systems and well, noise usually is all around.
Yeah.
We have external influences. So I think like usually in a real system, you'd have one of these mechanisms like a bifurcation or collision along with noise.
Yes.
And so would someone say like a hybrid mechanism?
Yeah.
Do you think we have methods to detect such hybrid mechanisms of transition with statistics and our current knowledge?
This is a good question. Of course, I have not checked this, but most of these transitions, so which I have discussed, are not disappearing because of noise. So you can still identify them with noise. They look a little bit different because the noise, of course, plays a role. So that you would see, for instance, possibly an interior crisis also before it really happens deterministically. So, but still, so to say, you might be able to identify what type of transition this is. So even with the noise, but it applies to all these mechanisms. If the noise is too large, forget it. So there's no way, I would say. So if the noise is too large, you don't see anything, and so because then you get probably also again to diffusion in state space, and then it's useless to look for transitions. But for moderate noise strength, even you might be able to do it. Yeah.
Do you have any specific methods, numerical methods, in order to deal with the noise itself? Because I mean, a system just can have the noise that the system permits. So I have a noise of a natural fluctuation of the system, but maybe noise is some type of a problem of measure. I mean, so I could decompose this noise in some type of, I don't know, of mathematical analysis in order to analyze this. I don't know if it was clear.
Probably you can do something. So there are noise reduction methods, for instance, so which you can apply. And so Klaus knows that much better, probably how to decompose perhaps noise, so to say, in different classes of noises. So because they act differently. And in neurons, this is also something which I tried out already myself in some models. So it depends crucially on where you put noise. So, then also the response to the noise would be different. And this is a very good question, of course. So because for all these mechanisms, so what people have done so far, I think, is only additive noise for all these transitions. I cannot remember have seen any multiplicative noise for all these crises and stuff like this. So it's all done with additive noise, then you still see things. But how it reacts on multiplicative noise, this is not so clear. So I know now we are working now on multiplicative noise, which even is correlated noise, not even so to say white noise. And then we see already that noise-induced transitions look different. The thresholds are even different. So this is what you can get in population dynamical systems, for instance. And this, of course, rings the bell already, so that one has really to go into more detail in the noise, and also go away from all this type of additive noise, because in many systems we need not additive noise, and also correlated noise. So now the people who are now trying to do these type of things in climate science, they definitely should take correlated noise. So with white noise, they do white noise all the time. Okay, so better not to do this, because this is not what the reality is. So more questions. Everybody hungry for lunch?
There's announcement. You may have already received an email